here for your teams or your organization's meeting. I always appreciate people giving me their time and them wanting to hear a bit about my story and my job and stuff like that. So hopefully I'll have some interesting stuff to talk about. And like I said, feel free to interrupt at any time. I'm just going to talk a little bit about myself and kind of what I do and where I came from. And I'll talk about the program that I work in, the Launch Services Program, the logo that you see here on the top right. And this logo that's on my shirt. And yeah, I'll talk about my job and the work that I do, and then a little bit about how I got here. And yeah, feel free to interrupt at any time with questions. So this is just a little bit about me. So yeah, I grew up in San Antonio, Texas. I'm a big Spurs fan. So yeah, I grew up there all the way through high school, and then I went out to Stanford in California for my undergrad, where I did aerospace engineering. And when I was there, I had my first NASA experience working at the Jet Propulsion Lab, or JPL, down in the Los Angeles area in Pasadena. So did that for one summer, really great experience. And then that was after my third year at undergrad. And then the year after that, I moved to Michigan to pursue a master's degree in aerospace engineering. And I was there for 2 years getting that degree. And I actually got sort of like a dual degree. So they had your standard aerospace engineering program. And then they also have a program called Space Systems Engineering. So it's like a systems engineering degree that's focused on spacecraft. So that was a really cool way to get some more hands-on experience. So after doing that, I went to Northrop Grumman up in Maryland. I mean, Northrop is all over, and they do a lot of different things. But I worked in some of their spacecrafts. It was basically a Department of Defense weather satellite program. I was doing some orbital analysis for them because I had really gotten into orbit mechanics after undergrad and grad school. So I did that for just about 6 months. So I kind of see it as an internship, even though it really was a full-time job. And that was because when I got there, I knew that I really wanted to work for NASA. So I was still applying for NASA jobs, even though I had already gotten a job at Northrop. And one came up a lot more quickly than I expected. So I ended up leaving quicker than I planned on. But it was a great opportunity to come down to Florida and work as a launch vehicle trajectory analyst for LSP. So I'll flip to this next slide where I just have some pictures of a little bit about what that journey was like. This one on the top left was me at the Goldstone Deep Space Network, or DSN facility in Southern California, kind of in the middle of the desert. So you can see my tiny little body right there next to this huge, I think that was the 70-meter diameter dish. So these are the dishes that we use to communicate with spacecraft at Mars, Jupiter, even the Voyager spacecraft that are out of the solar system at this point. They're still using these dishes to communicate with those. So that was a really cool place to be. Picture under that is me in grad school working on a CubeSat with a few of my fellow grad students. They might have been undergrads at the time, but there was a CubeSat lab that I got to work in, which was a pretty cool experience to actually work on hardware that has flown in space. So we were doing some of the early design analysis for a CubeSat that ended up launching on a Falcon Heavy just last year. So that was pretty cool to get to work on that. So one of the interesting things, growing up in Texas, I'm used to hot weather, and I'm sure y'all are too. And so I actually complained about California weather when I moved to California because I thought it was too cold. And then I ended up moving to Michigan, which was just terrible. So it was really, really cold. That was the first time I saw snow fall, was when I moved to Michigan. I was like, 22, 23 years old. So that was a pretty big challenge, but I made it fun whenever I could. And if you can believe it, the picture underneath that the snow one is actually a beach in Michigan too. So if you go north, like along the Great Lakes during the summer, it's really, really nice there. So that was one of my highlights of living there. And then these pictures on the right are from when I finally got down here to Florida. So on the top right, that's me and three of my coworkers. So we all got hired on the same day. And so we got to do a lot of our orientation stuff together, which was pretty fun. And it was cool to kind of have a team to, challenge each other and learn from each other as we were learning the NASA ropes. And sort of a cool trivia fact is that the elevator that we're in is the elevator that every single astronaut who's launched into space from the US has left the astronaut crew quarters, which is in the building that I work in, gone down that elevator, and then gone out of these those famous doors out to the Astrovan or to the Tesla now, I guess, when they're flying on the Dragon, with SpaceX, and then gone out to the launch pad. So it was pretty cool to be in that elevator that that has that much history. And then, like I said, I'm a big Spurs fan, so that's me down in Miami getting heckled by the Heat mascot when I went to a game down there a couple of years ago. So I wanted to start off just talking a little bit about the environment that I'm in at KSC. So this is on the Space Coast in Florida. So part of it is Kennedy Space Center, and then part of it is Cape Canaveral Air Force Station. So this is I think it's a pretty old picture from when there was like a lot of like missile launches out here, kind of in the early days before it was mainly a spaceport for space launches. And then that was the Cape side, and then this is just an amazing picture of the Kennedy Space Center side where you can actually see both launch complexes, 39A and B. So those are the pads that the shuttle launched on, and this picture just blows my mind every time I see it, because I never would have thought that they would have launched a shuttle with another shuttle on the pad, because like there's just like, and I'm going to talk about this a little bit later, but there's just so many different environments going on, all the acoustics and everything like that. So yeah, that surprised me. But if you fast forward to today, things like that are happening again with all the activity here at the Cape. So this picture was from September, I believe. It was, yeah, because it was right before, I think they called it Scrubtober, the month when like a lot of launches got scrubbed. So one of these was that GPS launch that just got off, or the vehicle with the GPS spacecraft in it that just got off the ground last week. And then one of them is one of the Starlink missions. So you see these two Falcons standing up on the pad. So this is 39A. This is pad 40, right? They have pad 40. And then down here to the right, you can barely see, you can just see kind of the top half of the Delta IV Heavy that had that NRO launch, or that NRO spacecraft. And this one still hasn't gotten off the ground yet. But so that's why we call Kennedy this multi-user spaceport, because rather than it just being about either NASA or the Air Force, there's all of these different customers, all these different companies now who own or lease different launch pads. So it's really exciting that, increases the launch cadence a whole lot, even when there are, particular challenges at one particular time. So this is just a little bit more about the lay of the land. I mean, I got this picture from, the visitor complex, so it's kind of cartoonish, but I think it does give you a good example of what's going on now. So you can see 39B, the one all the way up at the top, which is the pad that NASA is working on now to prepare for the SLS launch. And then 39A is so again, both of these were the space shuttle pads, but now SpaceX is operating on pad 39A. That's where they launched the Falcon Heavy and Falcon 9s. Underneath that, you see ULA's launch pad, Slick 41, or Space Launch Complex 41. So that's where they launch Atlas from. So when the Boeing Starliner is sending astronauts to the space station, they'll be launching from here. Right under that is another pad that SpaceX has, which is 40. And then ULA again has Slick 37. That's their Delta IV pad. And then if you go down even farther, you see these landing zones where the Falcon Heavy boosters come back, or even just a regular Falcon 9 booster when they do bring it back to land. The most recent time they did that was that Southcom 1B launch, the one that went polar from the Cape. And that was a really interesting one, because that's where this multi-user spaceport kind of really came into play, because we had multiple spacecrafts, or multiple rockets on the pad at the same time, and you were doing this unique trajectory where you were launching from this pad 40, and you were pretty much hanging a right after you launched. So there was a lot of discussion about making sure that they protect the spacecraft and the vehicles and the pads and just all the hardware that's really downrange of that. and obviously, nobody, they came to the agreement, and there was no, there was no actual harm done to any of these assets that are down there. But it was pretty interesting to see that kind of stuff happen. And then if you go even farther down, it's not on this, on this cartoon, but Slick 36, I believe, is where Blue Origin is going to be launching from. So there's kind of more stuff coming up every day. So this is another image of just kind of what this whole place looks like. And I added some labels on there just to give y'all an idea of kind of the lay of the land and kind of what it's, the stuff that's kind of important to me. So, I mean, you see where I live, this is where I am over here now. And this is now also where I work, because we've been, teleworking since March. I used to work over here in what we call the industrial area. And that's a pretty cool spot because there's a payload processing facility, or the PPF, which is like just right down the road from the building that I work in. So the Mars 2020 rover that I'm going to talk about a little bit later got processed here. And there's also a processing facility actually all the way out here on the other side of the river called Astrotech, where some of the other spacecraft get, their final testing and processing before they head out to the launch pad or wherever they're going to get mated to the vehicle, mated to the launch vehicle. If you go a little north, you see the shuttle landing facility. So this is where the space shuttles landed when they came back to Kennedy. And this landing strip is used for, different purposes now. We'll actually bring spacecraft to Kennedy, on this giant NASA aircraft. And they use different spacecraft use different vehicles, but a lot of them will land here on the SLF, which is always pretty cool to see about. Blue Origin and their rocket factory is right out here, just right outside of our gate. So it's pretty exciting to see that building come up and see them preparing to start operating out of here. And then just the last part is this little causeway. This is where I normally like to watch launches from, kind of in regular, when times are more normal, because you can just pull over on the side and you see how close you are to definitely Slick 37, 40, and 41. And you can also see really well from pads 39A and B as well. And I guess, nothing's launching from 39B right now, but when it does, this will be a great spot too. Oh, and the reason I actually won't talk about that now, but the reason I had this link here was because so this is the SpaceX failure from a few years ago when they had when their launch vehicle, they had a launch vehicle failure on the pad 40, right? I keep on flipping the numbers, but when they were on pad 40 and the vehicle blew up, that was actually a day right before not the day before, but it was right around the time when OSIRIS-REx, I don't know if y'all were following that spacecraft, but that's the one that just did that touch and go to grab a sample from an asteroid, and it's about to bring that sample back to Earth. So it was right before that spacecraft was, in the final phases of its launch campaign. And so we actually had people on launch pad 41, getting ready for that when this Falcon 9 exploded. So it was just really interesting. You can just imagine, being that close to it. And nobody got hurt, but I do have coworkers who were actually there that day, and they had to follow all of their contingency plans to, get to a safe spot and make sure that they weren't, hurt by any plumes or anything like that. So, thankfully nobody got hurt, but yeah, those are just the things that you have to be aware of when you're doing, dangerous operations like that at a multi-user spaceport where there's a lot going on. So it was interesting seeing how they adjusted to that. I think they changed their operations. They no longer do the hot fires with the spacecraft in actually on top of the rocket. And they're also not going to do that procedure while there are other vehicles, being processed on adjacent pads. So these are the things that you learn when, when really transforming a place from a place that's mainly about the space shuttle to a place that's about a lot of different launch vehicles. So now I'll sort of transition and start talking more about the launch services program. And again, feel free to interrupt me if you have any questions. but I'll start off talking about LSP. So our sort of tagline is that we are Earth's bridge to space. And the reason we say that is because we're the people who basically work with NASA's spacecraft providers or spacecraft developers. So the people at JPL, Goddard's, people at universities. A lot of the times it's, maybe run by a particular university or by a particular center, but there's collaboration with people potentially all over the world. So we work with them and the commercial companies that build the rockets and make sure that those rockets put those spacecraft into space safely, on time, on cost, and efficiently and everything. So, this sort of diagram that you see at the bottom shows what our mission support looks like. And, the thing I really want you to understand here is that it's a pretty long process. So the spacecraft itself, they could be working for decades, maybe not decades, but over 10 years to prepare or to get ready for a mission. And we may be involved in those early phases, and I'll talk a little bit about that later. But we really start to get into the meat of it in the last 3 or 4 years before launch. So that's when they're doing the final mission planning, baselining what the mission really is. And by baseline, I mean it's really having a solid understanding of what your operations are, what all of your goals are, and how you're going to achieve the science that you want to achieve. And one other thing that I'll specify is that these are only for the non-crewed missions. So these are only for spacecraft that don't have people in them. So we're not doing anything with the Crew 1 launch, but we are working with the Sentinel-6 MF launch, which is coming up just a week after Crew 1, also on a Falcon 9. So when it comes to a few years before launch, the spacecraft folks come to us and they basically tell us everything that they need, and we figure out which rocket is going to be the best for their mission. So we work with our contractors, which are ULA, SpaceX, and Northrop Grumman. Those are the ones who are on our contract right now, and figure out which rocket is best, and we actually buy that launch service. And then over those 3 years, we do what we call mission integration, while the spacecraft and the launch vehicle are actually being put together. And we just make sure that all of that planning is really in line. Some of it is more hardware focused, some is analysis focused, and I'll be focusing on the analysis side of things because that's the world that I'm in. And then in those last few months, we're doing launch site operations, and we're really in the launch campaign. And then we may be involved a few months after launch, but basically once launch happens, our job is done, and we move on to the next one. So yeah, this is a picture of a Falcon Heavy launch, and I wanted to talk just a little bit about what I mean when I say the launch vehicle environment. So obviously, you imagine building a spacecraft, you spend 15 years developing all the science instruments and putting it all together into one spacecraft, and then you have sort of all of that converges onto this one moment when you're going to strap it on top of a rocket and light this super violent explosion to try to get you into space. And there's just so much that you have to account for. So there's accelerations, static and dynamic. You have your acoustics and vibration. So there's a lot of that going on, especially because of the environment in the fairing. You have potentially a really complex thermal environment that is changing over time as you go from potentially waiting on the pad for a couple of hours. If it's a sunny day, you may be getting really hot, and you have to be aware of what's going to happen. And then you get into space, and it's completely flipped. Once you've taken off the fairing, once the fairing has been jettisoned. There's electromagnetics, things interfering with one another, especially since you have one complicated system, which is the spacecraft, and another complicated system, which is the rocket, and you have to make those pieces go together. Then you have shock, which is sort of the event that happens when things like the boosters separating, the stage separating from the first stage separating from the second stage, fairing coming off, spacecraft separating, engines shutting down, all these things that could shake the spacecraft in a way that damages it. So we have to really have a grasp of all these things. So I've been good so far at having mainly pictures on my slides, but I did want to include this one because it really or it may be of benefit to any of you who may be interested in doing this type of work, because it shows what different engineering disciplines we see and just kind of what major that goes to. So I'll send you all these slides, or maybe just this one, because this is the one that has actual information that you can look at. But on the left side, you see everything that's in the analysis world. And on the right side, you see everything that's more on the engineering, hardware focused world. So I'll go over these pretty quickly, and then focus on one of them in particular. So flight design, we look at the performance of the vehicle and the trajectory. G and C, that's related to the controls, the control systems design, your navigation, accuracy, steering, and your flight software, which is how you actually develop code that's going to implement all those different algorithms. You have coupled loads and environments associated with how your hardware is interacting to the vibration environment, the acoustic environment, and the structural dynamics. You have propulsion, so that's literal rocket science, I guess. And then you have EMI, EMC, which is the electromagnetic interference or compatibility, which is what I was just talking about on that last slide. And then on the right side, we have other people who do more of the payload side, so mechanical and electrical engineering for the spacecraft itself, and all those hardware pieces, making sure the stuff is literally fitting together and not going to do any undue damage. We have a hangar out here for people who are doing all of the planning for being able to communicate with the rocket and the spacecraft during the launch. And then ground processing as well. So that's things happening at those PPFs, the payload processing facilities that I talked about before. You have to make sure that everything is going to keep the spacecraft safe for the potentially few months that it spends at KSC before it's actually time to launch. So maybe I'll pause here. Does anybody have any questions about any of this stuff before I dive into flight design, which is the one that I do?
Yeah, guys, go ahead. I do have a question regarding, for example, if you're an intern, do you have any opportunity in working in one of these disciplines at the launch services program?
Yeah, so we have interns all the time. We actually fairly recently had an intern who worked with us for like 6 months, and then she went back to school, and then got hired full time like once she finished her degree. So we definitely think it's important to be able to we think it's important to be able to provide opportunities for new sort of fresh out engineers to be able to contribute. And I think that the current environment that we're in with just new vehicles coming up, like there's a lot of things changing for LSP. So I think it's pretty easy for our groups to find projects for interns actually be beneficial. So we've had people do a lot of different stuff, modeling for at least for the flight design group. I know we've had people do modeling for the Falcon Heavy. Like we just awarded our first Falcon Heavy to a NASA mission just a few months ago. It's going to be on the Psyche mission. So since we haven't flown that vehicle yet, we didn't have much modeling of the Falcon Heavy. So we had one of our interns put together a model that we're still using today, almost a year later, to help us understand that vehicle. So yeah, and I can maybe talk about that more in general later on. But the Pathways program, the Pathways internship program, is definitely the best way to make that happen.
Perfect. Thank you.
Great. So I will move on. So yeah, now I'm going to focus on flight design, which is my job. So this is sort of another way to look at that timeline that I showed before. So for the spacecraft, they have all these different phases that they go throughout their lifetime. So you start off with your concept studies, and you're really just kind of on a high level. What are we trying to do? What science do we want to get? How do we want to go about getting that information? And then you're potentially developing your concepts and your technology and putting your preliminary design together. And during that time, it may be helpful to know what your trajectory is going to look like what your path to space is actually going to look like. So they'll come to us and maybe ask about vehicle performance. So what's the lift capability of the rocket, so they can know how much mass they'll be able to, or like what limit they should place on their spacecraft for mass. And there's obviously a lot of other considerations there too. Cost is a big thing. So if they already know how much money they have for a rocket, they can anticipate sort of what class of vehicle they may fly on, and then we can stand up a model to show them what the performance may be for that. And then we'll also come up with our own trajectory design based on what we know of the vehicles, so we can tell them. So obviously we can't make a commitment for the launch vehicle company, but we can say, yeah, we expect it to take 50 minutes to get from launch to separation. We expect your trajectory to look like this. We expect there to be 10 minutes between, when you start your burn and when you enter eclipse, like when you go behind the Earth, relative to the sun. So all those kind of, advanced mission support that's a big part of what we do. And then we're a part of the procurement process. So the part of, buying the actual rocket, once we know which one is going to be best for your given mission. And then we work closely with the spacecraft and the launch vehicle team to make sure that everybody's processes are lining up, and to make sure that the spacecraft understands the launch vehicle and the launch vehicle understands the spacecraft. So we really just want to be NASA's group of people who understands these commercial rockets, because the commercial companies can, things change all the time. And so not only are they, changing and adapting and growing and innovating, and we want to keep a grip on that, but we also want to be sort of a common source, because the NASA spacecraft can be huge differences in what a different spacecraft needs. So we want to be able to make sure that that we keep them realistic based on what the launch vehicle can do. And then, like I said, after the flight happens, we review the post-flight data, after the launch, to make sure everything went the way that it's supposed to go, and then we move on to the next one. So this is sort of an analogy that I normally use for trajectory design, to sort of, if people aren't familiar with the idea. So there's 4 steps that we go through in order to really build up our trajectory. So the first thing, and you can use this this analogy of driving a car from A to B on the road. So you imagine your trajectory events. So there's a particular number of curves that you're going to have to go around in order to get where you're trying to go. Then you have constraints. Those can be speed limits, particular places where you can't go, a school zone where the speed limit is different than where it would normally be. You have your controls, which is obviously your steering and then how fast you're going. And then you have an optimization parameter, which is some measurement of your efficiency, or it's something that you want to maximize or minimize. So if it's not the amount of so I'll talk about that a little bit later in the launch vehicle. So in your car, that's normally going to be just gas. Make sure that that you're gas efficient. So when it comes to a rocket, that obviously looks a little more complicated. So these are what the trajectory events may look like for an Atlas or a Falcon 9. So you can see all these different events that are going to happen for every vehicle. If it has solid rocket boosters, that's one event. When those things jettison, the first stage separating for Atlas, that's called BECO. For Falcon, that's called MECO. Those Atlas, they call it booster engine, and then for Falcon, they call it the main engine cutoff. You have the events when the payload fairing separates, when the second stage engine starts up and cuts off. So you have all these different events, and obviously based on the complexity of the launch vehicle, you may have to do different things. So for the Falcon 9, we have a whole extra set of trajectory events that are based on the recovery profile. So we'll model this as well, the boost back burn, the reentry burn, and the landing burn, and everything associated with that. So those are your trajectory events. Then you have constraints. Obviously, weather is a big constraint. I think this was from DM1, the first demo mission of the Crew Dragon from last March, like not this year, but last year. There was just this huge, set of clouds off the coast. but fortunately it wasn't in the path of where the vehicle was actually going to go. This picture on the top right is actually from the space shuttle days, and you can see that because you see SRB impact, the solid rocket boosters, the ET disposal, which is the external tank if they were launching from the West Coast. They never did that. But you see on the East Coast this allowable launch azimuth range, which is basically the angle that you can launch at or launch out of, which changes based on the vehicle and based on what's happening at the Cape. But obviously that that can be a particular constraint because you don't want to launch over populated land. And then on the bottom, the best way that I thought to come up with this constraint about acoustics and dynamic environments is to just show this picture. This is of the Parker Solar Probe when it's actually getting tested for vibration. So it's on a shot or it's doing a vibe test here. So obviously, if you're stacking this spacecraft on top of this rocket that it's executing this really violent event, you want to make sure that the rocket is not going to shake the spacecraft apart. So they may have to add hardware or throttle in a particular way to avoid damaging the spacecraft. So those are your constraints, and then your controls. That may be a little more intuitive. You can think of just a regular sort of free body diagram type of thing where you know where you're trying to go and how you're trying to control it. Obviously, for a launch vehicle problem, it can get pretty complicated when you want to implement the wind, different disturbances. But at the end of the day, one of my coworkers normally says that flight design is pretty easy because instead of having to do a bunch of stuff that's super complicated, it's really just the pointy side is up and the fire end is down, and then you're good to go. You're going to go up to space. And obviously that fire side going down is how we control where the rocket's going to go, because you are controlling that thrust vector. But then, also just based on what some of the new capabilities are, you have a different problem, which is, putting your pointy end up and the fire side is down, but you're actually trying to land on this landing pad. So this introduces a new control problem that is, or I guess just a more complicated control problem that's pretty interesting to see happen. And then, based on the priorities of the company and the way that they operate, you could have different control problems too. So this is a diagram that shows what it looks like for ULA to implement their algorithm that they call RAN steering. And it's basically a way of making sure that you can get to the same orbit, at the correct time or in the correct timing, even if you do not launch at your optimal time. So even if you launch an hour before, the best possible time in terms of performance, you can still steer your vehicle around in order to make sure that you intersect the correct orbit plane. So obviously, if you've taken an orbit mechanics class, maybe you can imagine how if you wait for 30 minutes, your orbit plane is going to tweak based on the rotation of the Earth, and you might miss the International Space Station, and you don't want to do that. So that's a pretty interesting tool that they have to be able to control the vehicle that way. And then the last step is your optimization parameter, as I said. So that can be it can be something about timing. Maybe the spacecraft says that they want to get to space in less than an hour. Because of the batteries that they have on the spacecraft, once they are on internal power on the launch pad, they need to start getting solar power pretty quickly. So they need to separate from the launch vehicle before a certain amount of time. So that can be something that we look at, or it could literally just be about the lift capability of the rocket. So here on the left, you can see the Mars 2020 spacecraft getting encapsulated on the Atlas V vehicle, or on in that fairing, the 5-meter Atlas fairing. And then on the right, you see this big batch of Starlink satellites getting encapsulated into the Falcon 9 5-meter fairing. So yeah, I wanted to talk a little bit about Mars 2020 because that's a mission that I had the pleasure of working on over the past couple of years. So yeah, I think you saw this picture at the very beginning of my slides, but So you see there's me right here, and then the Atlas V is right behind me, because I actually had the opportunity to be there on the launch pad the day that they rolled the launch vehicle from the VIF, or the vertical integration facility, out to the launch pad. So I was standing right there at the end of that arrow just a couple of days before launch. That was a pretty awesome experience. So when it comes to the actual trajectory design for Mars 2020, you get to see some pretty interesting stuff. And I think it's always cool to look at this, because you just see everything that comes into designing an interplanetary mission. So if you're not familiar, what you're looking at here is called a pork chop plot. And the reason it's called that is because I feel like it's kind of zoomed in here, so you can't really see the full shape. But basically, the way that these plots work is you essentially say, for a given launch date and a given arrival date, how much energy is it going to take me to get from planet A to planet B? And knowing that planet A and planet B are in different orbits, so your timing matters. So it's going to be different if I try to launch if Earth and Mars are right here versus if Earth is all the way on the other side. So you basically do that calculation, and you can figure out for every pair of launch and arrival dates, what does the energy look like? And you want to find the minimum energy so you can have the maximum payload mass for a given vehicle type. And then you could also throw a bunch of other data onto this plot. So for a given launch and arrival date, you can see what the communication with the Mars Reconnaissance Orbiter looks like. So that's what this shaded sort of yellow region is. And then the purple is when, just due to the where the planets are and where your spacecraft is going to be on the path, you can have this full direct to Earth communication. So that's something else that they look at. So based on your priorities, you can make decisions on when you want to launch and when you want to arrive. So this is the pork chop plot for Mars 2020, or the Perseverance rover, where you can see how they ended up with our launch period, which was July 17th through, ultimately it ended up being through August 15th. And the launch day was actually on July 30th. So, all these contour lines are basically showing you how much energy it's going to take you to get there in units of C3. And something kind of cool that I actually just realized about this slide is that it's actually overlaying the maximum energy based on the vehicle performance. So this, where it says PMA response, that's the preliminary mission analysis, which is an analysis that we got from ULA when they were designing the mission, and we were doing all of that verification that I talked about. So they said, for your spacecraft mass of 4,147 kilograms, we can hit this C3. So we want our entire launch period to fall within that range. And at that time, we had not extended all the way out to the throughout all of these supplementary days. So we still had a 20-day launch period, perfectly within that contour that we were looking for. And then just another thing that's cool looking at this plot is that you see the dust season. Like, they're you obviously don't want to arrive on Mars in the middle of a dust storm. These planet-sized dust storms where you're not going to be able to, have any, like, you're not going to be able to see anything because of all the dust. So it's pretty cool to see something like that on the plot as well. So this is a chart that I looked at a lot over a couple of years because it actually showed our targets. So really what we had to do, and one of the things that makes my job important, is that we want to make sure that we get the spacecraft into space safely. And if you're going to do that, you have to recognize that things aren't always going to work out perfectly. So you want to do as much planning as you possibly can. So one of the things that is unique about both JPL and ULA is that they have their processes worked out in a way where you can have a lot of different launch opportunities. So we had upwards of 2 hours worth of launch opportunities every single day for the first few weeks of the launch season. And then, the duration of the launch window started to decrease down to just 30 minutes on the last day. But, the point is JPL chose to give us different targets depending on what exact time they launched, because they wanted to minimize the amount of propellant that they had to plan for to do trajectory corrections. So, if you imagine launching at a particular time and, you're going to Mars and you launched 1 hour later than you wanted to, but you still launched successfully, you may have to use a little bit more fuel to get right back onto that perfect path. So they just defined the perfect path for every 5-minute increment, which meant that we had like 600 trajectories to verify over those 30 days. So you can see how those targets, you see open, middle, close. So that's just 3 of the targets for each of the days. But those are separated by maybe an hour as opposed to just a 5-minute increment. So that's how, and that matches well with the fact that ULA is able to do that RAN steering, so they can still launch. They can launch. They're able to support a 2-hour operational window because of just the way that their vehicle is set up. You can load up and wait for those couple of hours. You can load up in terms of the propellant. So this was a really interesting experience for me because it was my first launch campaign, and it was this year. So we know that there's a lot of challenges associated with the pandemic and everything, and there was also an issue that they found on the launch vehicle coming up in the last few weeks before launch. So we actually ended up losing the first 13 days of the launch period due to COVID and due to some issues on the launch vehicle. So your heart starts racing a little bit, and you're like, wow, we've analyzed 30 days and we lost almost half of them already. But fortunately, the engineering teams did a great job of identifying all the problems while we were planning for maybe being able to extend past the 15th of August, just in case we had more delays. But fortunately, it got off the ground right at the beginning of the window on July 30th, and it was really a beautiful launch. And this is, just that same type of plot, but what it looked like for the Mars 2020 rover. And this is just sort of a really cool video that I wanted to, oh, that's embarrassing. Let me open up. I'm gonna have to exit out of I always forget that my automatic, what is this? Sorry, I gotta change up my sharing really quick so I can show you. Let's see, screen number 1. Okay. So yeah, this is my Twitter page, but I just thought it was really cool that this is the live shot of the spacecraft separating from the launch vehicle. So that was really awesome to see. This is the shot that kind of shows us that we've done our job, and now the spacecraft is on its way to Mars. And you see the little things, like you see how it looks like the spacecraft is spinning up, but what's actually happening is the launch vehicle is de-spinning. It's spinning down because they were both spinning at, I believe it was 15 degrees per second. And then the launch vehicle had to slow down that spin so we could sort of stabilize and then get out of there. So it was no longer going along the same path as the spacecraft. Okay, so I'm almost done. So I only have one more slide. I'm gonna switch this up one more time. Come on, it's really slow. Okay. So yeah, the last thing that I wanted to talk about was just kind of, how did I get here? I kind of talked in general about, the different schools that I went to and stuff like that, and me getting my job. But I thought that this was a really good diagram to look at. So this is, JPL's engineering design process. And, so this is when they're, building a rover or a spacecraft or, solving some problem. And they say they go through the process of identifying the problem, brainstorm solutions, select a design, and then you get into this triangle of build a model or a prototype, test and evaluate, optimize the design, and you keep doing that. Part of that is, sharing the solution, and maybe that's just a part of evaluating, excuse me, after testing to, figure out what works best, and you get into this triangle. And I think that this works really well for, building your career as well. So I think this is important for, college students to think about, especially since there's, or at least I felt a lot of pressure to know exactly what I wanted to do and like get on the path towards getting me there. And I stressed myself out a lot by not being very willing to take risks and not being willing to commit to something if I didn't know for sure that it was what I wanted to do. So I actually got stuck a lot in in the second and third step here, in the brainstorming solutions and selected design. And obviously here, like, I'm not talking about an engineering design, I'm talking about planning my career. So, instead of identifying the problem, you know, it's asking the question of, what do I want to do? Um, so I definitely want to encourage you all to, do some brainstorming and asking questions and research, like, especially if you're in just your first couple of years. That's a great time to just see what other people are doing and see what piques your interest. And then pick one and just do it. So spend most of your time here in the trying stuff, evaluating, figuring out what works well for you, what you like and what you don't like. And that is where a lot of the development comes, a lot of the growth comes. And it's important because it's just as good to know what you don't like as it is to know what you do like. So yeah, definitely encourage you to, apply to internships. And if you don't get the one that you want, but you do get an internship, if it seems remotely interesting to you and, the finances work and the timing works, I would say just go for it, because it can definitely be valuable. So yeah, that's all I had. So I can stop sharing and open it up to questions.
Thank you. It's certainly been fantastic. We do have some questions. I think I'm receiving feedback from some, so I'm not sure. Let's see. There we go. I'm not sure why you guys cannot enter the chat, but as I told you via the WhatsApp chat, you guys can unmute yourself and ask your question to Philip. I'm gonna read some of the questions that I've been receiving. The first one comes from Giovanni, and he asked, "What's the dynamic of dealing with multiple launches in a short period of time? What are those challenges, and how is it all planned with the flight paths of each launch and their systems?"
You said with the flight path of all the systems? Was that the last part of it?
With the flight paths of each launch, and yeah.
Yeah. So I guess I'll first talk about sort of the planning phase. So one of the things, we don't always have, a million launches happening at the same time, but we do know that can happen, especially if it doesn't always start off that way, but sometimes they just end up stacking up. I think 2018, we had 5 launches in 1 year, which was a lot for one program. So, the managers, they do really well at looking ahead and making sure that people aren't kind of getting set up to end up having 2 launches at once, because there's a lot of reviews, a lot of management meetings where we have to, sort of report to like big NASA people to make sure that they know that everything is on board. And then also things come up at the last minute. So for Mars 2020, we had to analyze new launch dates within just a couple of weeks. And that came out of nowhere because we didn't expect to lose the first 13 days of the launch period. So I think it's all about preparation. And a big part of that is like documenting. Like taking good notes and having good processes that you can come back to quickly. So I think recognizing that things may change and you may have to redo your work. So it's like, it's worth it to make comments on your code so you know how it works. Like I ran into that problem a few times where I had to go back and rerun a script that I had put together once, and I barely remembered how it worked. So I ended up having to use a lot of time to relearn how to use my own stuff. So that's sort of the planning side of things. And then when it comes to like just like physically the launches, really there's a group called the Range, which is like the Air Force side of things at the Cape, who really handles all of that. So they have protocols associated with like the time between certain launches and stuff like that. But yeah, like space is pretty big, so we're not going to have things like crashing into one another. Like they're not going to be launching that close. But yeah, it is a pretty interesting problem, especially when you have multiple things launching in 1 week. But yeah, so hopefully that answers the question.
Right. I have some questions for myself, and I think you already answered this, but what's the favorite launch you have working?
Mm. Well, yeah, I mean, so Mars 2020 is the only one that it's the only one that's launched so far that I've like directly worked on. So I guess it has to be that one. But yeah, I mean, the Falcon Heavy, I remember the Falcon Heavy demo launch like it was yesterday. That was one of the coolest experiences ever. I love watching the Atlas launches with the solid rocket boosters because it gets off the ground so fast compared to the liquid ones. Yeah, and then it's like every launch is unique. There's the early morning launches where you if you launch right before sunrise, you're in the dark, but by the time the vehicle gets high up into the air, it starts to hit the sunlight. So it lights up and you see this huge, like, it's like something's, getting painted in the sky. So, it's always really cool to watch different vehicles.
Right. And now the other question that I had, how is LSP preparing to support Artemis? What's your level of involvement that you are looking for with the Artemis program?
Honestly, I should have a better answer to that question. I don't have a great answer to it because I haven't been directly involved. I know that we've been involved in, Gateway in terms of being a part of evaluating the commercial proposals for the vehicles that are going to be supporting Gateway. And yeah, I don't know all the inner workings of how it connects to how it connects to Artemis, but I think in general, our launch vehicle expertise is, our goal is to be able to support, whenever commercialization is a part of Artemis, and and also, the science that's done on the spacecraft that we launch is supporting um, the human space flight in terms of being able to better plan for where we're trying to go.
Right. Nice. So guys, I want to open up to you. If you want to unmute yourself, you can do so now and ask any question that you have. So go ahead. I'll give you guys some seconds to start unmuting yourself. Come on, don't be shy. Priscila, Rebecca.
What's a piece of advice that you would tell yourself in your college years if you could?
Well, yeah, I think what I put on the last slide is what I would tell myself. It's like just to take the risk of doing something. I closed. So when I worked at JPL, I was in the mechanical engineering group, and I found out, like, I had learned that year that I was really interested in orbits and trajectories. So I was like, I got to work in the trajectory group. I got to work in that group, and like I'm pretty sure that I would have been able to get hired in the mechanical group again, full time after graduating, but I like didn't pursue that because I only wanted to do this one thing. So it's like, yeah, get in the door however you can. And that doesn't mean to sell yourself short, but yeah, if you can get in the door, especially if you're talking, NASA, it is difficult enough to find that opportunity. So yeah, just be open to maybe that. So maybe that's the advice. The advice is be open to new experiences, and yeah, challenge yourself to just always keep learning stuff, learning new things.
Super.
Thank you.
So I have a question that just came up. So you're working at NASA now, but what are your future plans? Do you expect to remain working at NASA, or are you pursuing, for example, a PhD degree somewhere after some time has passed?
That's a great question. It's in work. I'm not 100% sure. I love to teach, so I've been teaching orbit mechanics classes at Florida Tech for the past couple of years, and I really like doing that. So there's a chance that I'll end up doing a PhD so I can teach more often than not. But yeah, right now I'm focusing on being able to support the launches that I'm working. I'm working on a couple of missions that don't launch for a few years, but it'll be really great to see them go. So yeah.
Perfect. Guys, go ahead with more questions. We have a couple more minutes to go. So I have a curiosity. For example, I think that something that for at least in our university is not like it's not taught. Like we don't have any classes for that. What kind of advice do you have for people that want to learn orbital mechanics and flight trajectories of engineering on our own? Because we want to certainly have that expertise, go to NASA or to Lockheed Martin or to whatever company we go to, but sometimes it's difficult to get those resources and learn. So what do you suggest we can do?
Yeah, that's a good question. So some people, I think a fun way to do it is, I don't know if you've heard of the game Kerbal Space Program, but like you may be surprised at how many people like that's their real answer for like how to learn orbit mechanics, is to play that game. I actually started playing the game a month before I got my interview for this job like 4 years ago, so that was kind of a cool coincidence. There's also a program called GMAT, like GMAT, that is freely available, and you can like that's a really good orbital analysis tool. It's made by NASA, which is why it's open to the public. So you can use that to do your own simulations, and they have a bunch of sample problems in there that you can learn about all these things and how to do maneuvers and optimizations and stuff. So that's a pretty good tool to use as well.
Let's see. Anybody has a last question before we part for tonight? Right. I have a question from one of my colleagues related to the things that you just talked about. She's asking if you would recommend STK as a modeling software for flight systems.
Yeah, STK is great. The only reason I didn't bring it up is because I don't know how much it costs or like how easy it is to get it. Maybe as a student, it's easier. So STK is the one that I started off learning when I was in grad school, and then in my office we use one called Free Flyer, which is put together by AI Solutions, which is one of our main contractors. So yeah, STK and Free Flyer are both great tools as well. And actually, I do know that for Free Flyer you can get a like a student license, and I'm sure STK does the same thing if you have a .edu or at whatever .edu email. So.
All right. So the last question would be, what advice would you give to students, specifically our group, that are in their undergraduate studies and are looking for opportunities in graduate studies, like advice to go to grad school?
That is, yeah. When I think about advice I would have given myself, yeah, I needed to have been a lot more prepared for grad school, or maybe I'll just say I had a lot of challenges because I could have done a lot more research on just kind of what it's all about. So I went to grad school because I just knew that I wanted to get some more like project-based experience before getting into a job. Maybe talk to as many professors as you can to see what skills are needed by grad students, what opportunities are at the school that you're at, is a really great place to start. And yeah, I think just like talking to people in grad school and talking to people who are in academia will help you understand if you want to do more of the research side of things, or if you want to do more of the project, like work in a lab that builds CubeSats or satellites or whatever. But yeah, I think it's good to know what you're doing before you do it. So yeah.
Perfect. I think that will be all for today. I want to thank Philip for taking his time to come talk to us virtually, of course. It's been great. I've learned a lot, specifically from Kennedy Space Center and the LSV program. So thank you for that, Philip. And you guys can follow him on Twitter if you want to drop down your ad in Twitter. He's on Twitter, so you can follow him. And for you guys, remember to fill the attendance form and be ready for our next Space Talk, which will be on this next Thursday with Daniel Alvarado, an ex NASA engineer, and he'll be talking about satellites. So thank you again, and good night, everybody.
Thanks so much for having me.
Thank you, Philip.
I'll take care.